Thanks very much. So now let us move ahead with the first keynote talk of the conference. So it is my indeed great honor, to introduce our keynote speaker, Professor John Grundy. John Grundy is a laureate fellow of Australian Research Council, very prestigious fellowship that Australian government awards just 20 per year across all the disciplines that humans are pursuing. So that is very prestigious one. So that laureate fellowship is primarily focused on human-centric software engineering. And I requested him to speak about that aspect and how I relate that to, IoT, cloud, and edge computing. So apart from that, he is a professor of software engineering at Monash University right now. So before that, he held various leadership positions in different universities in New Zealand. So there he served in various roles in New Zealand, in University of Auckland, as head of School of Electrical and Electronics Engineering, led software engineering project initially there. After that, he moved to Australia. In Australia, after moving to Australia, I think almost close to 10 years, I guess. The moment he moved to Australia, I was also fortunate to meet with him at Swinburne University. So there also he led the schools in building software engineering stunt programs. Then he moved to Deakin University, where he was pro vice chancellor, looking into digital innovation across the university. After that, he moved to Monash, and there he was a senior dean. So now he moved towards full-fledged focus on R&D innovation from various community leadership. And he was also president of something what we call CORE, Computing, Research and Education, Australia and New Zealand, Australasia. So many of you know that, ranking of conferences and journals around the world, CORE ranking is very prominently used by. So John was the leader of that organization called CORE that does this ranking of conferences and journals. So he has mentored many students who themselves went on to become leaders in industry and academia. Then with this is a laureate fellowship, so he is really pushing very hard, deeper into software engineering aspect, how to build software systems that are easy to use, not just for youngsters but also those who are maybe not that savvy, that very expert in using software, but still how can we build them and how can we build them in productivity. All that will be talk of as will be focus of his keynote. So John, thank you very much for our accepting invitation to present the keynote for CC Grid. So with this brief introduction, I like to hand over the control to you.
Thanks so much, Raj. Thanks so much to the committee for inviting me to give a keynote. It was actually for CC Grid 2020, but a year late, that doesn't matter. Our thoughts go out to all of you around the world that have been badly impacted by the COVID-19 pandemic, particularly any of you in India at the moment. We really feel for you and hope things will improve very quickly. Just a brief acknowledgement of country. So there's something we do here to acknowledge the traditional owners of the land. So as we gather for this meeting, physically dispersed and virtually constructed, let us take a moment to reflect on the meaning of place, and in doing so recognize the various traditional lands in which we do our business today. We acknowledge the elders, past, present, and emerging, of all the lands in which we work and live, and in their ancestral spirits with gratitude and respect. I'm actually in lands that the traditional owners are the Wurundjeri people of the Kulin Nation, so that's where my house is, where I'm giving this talk from today. So I acknowledge those peoples. So what I want to do is talk about software engineering and humans. So believe it or not, humans are users of software and they're also involved in the building of software. Then I want to give you some examples from some of our work. Some of them are very directly connected to kind of cloud and grid applications. Some of them not so directly connected, but you can probably see the connection to the conference theme. So I want to give you a flavor of some of these kind of human aspects that have a large influence on how we go about building and using software systems. And I want to highlight some areas where we haven't kind of got it right yet, or haven't figured it out yet. And so I'll probably be told to sort of finish up by that stage. So I'll briefly talk about kind of some of the things we still need to solve. So software engineering and humans. Well, this is a diagram I used to use when I used to teach introductory software engineering. So it kind of lays out the kind of traditional phases of software engineering. And one of the things to observe is that humans are present all the way through. So we write code and test code. Humans design software. We have to talk to end users or stakeholders to figure out what the software should do, requirements engineering. We have to work in teams, so we need project management. We need tools and methods to support this kind of stuff to get it done. And ultimately, people use software. So normally we don't just build software for fun, for the heck of it. We're trying to build software to solve human challenges, solve human problems. Now, there are, unfortunately, lots and lots and lots and lots of examples of where we kind of forget about this human aspect, both when we're building it, so humans as builders, as team members, if you like, and humans as users or stakeholders in the software system. So there's lots of really bad examples of gender bias. So the one I think, actually there's lots of bad ones, but one particularly bad, seatbelts. So seatbelts are designed for the average size male. Now, why is this? Because all the crash test dummies are average size males. So they obviously aren't so good for women, because women are obviously different to men, but they're not good for large men or small men either. Lots of UIs have gender biases. So men and women, the way their brains solve problems is different. And because most user interfaces are designed by men, there's a way of going through and, if you like, problem solving with the interface that tends to better suit men than women. So there's actually a really nice tool called Gender Mag that's been developed by a couple of my colleagues at Oregon State University that you can use to highlight gender bias and UIs. Very interesting. Ethnic bias, we've all heard outrageous examples of software systems that fail to recognize people of certain ethnicities who, when police are kind of trying to use AI to kind of do policing kind of circuits in cities, they kind of over recommend minority areas and that sort of thing. Lots of cultural bias where we use the wrong images, words, phrases, etc. That are fine in one culture but totally inappropriate in another. Lots of interesting language bias. So we as software developers use lots of technical words, and sometimes they creep through into our software interfaces. So we use words that most people, most normal people, dare I say, wouldn't use, but we do as software folks. Use the wrong dialect, make it impersonal, have it in a language that's not your native tongue. So you might not have proficiency in the language, the app or the website or whatever it is written in. A lot of age bias in software. So we recently had a really interesting study about age bias in online shopping websites and apps, which is very interesting. So very, very biased. And part of the reason is generally there's softwares like most else built by young people who have a certain perception of what everybody wants from online shopping, but it's not the same as many others. Many people have physical challenges that often is sight, hearing, maybe motor skills, etc. There's a lot of cognitive bias in software, so where the software is a poor fit to the user's mental model, and it makes it really difficult to interact with and to problem solve with it. Enjoyment bias, some of my favorites. Software is boring or not fun to use. So most of us like to use fun stuff, right? So why is so much software that we use for doing kind of lots of our work and living tasks so boring? A lot of software can introduce quite a lot of stress. I'll actually show you a smart home example shortly of how software can introduce a lot of stress to certain end users, and we need to better understand that and better manage that anxiety-inducing aspect. So particularly in software for kind of situations where you're trying to deal with emergencies and so on. A good example of bushfire software that we had here, the apps turned out to be totally unusable when people are under stress in the middle of trying to evacuate in a bushfire. And then interesting one, personality bias. So we all have different personalities, and again, if the software is not taking cognizance of that, you can end up being lack of engagement, lack of enjoyment, lack of disconnection from the software. And there's many other biases as well that turn up. Now, I'll just re-emphasize, these can apply to the team as well as the user. So my group is very interested in software developers or software engineers as humans. So that's the team impact. So how do different genders, ethnicities, language, personalities, emotions, etc. impact the doing of software engineering? But we're also very interested, of course, in the user perspective, so the people who use the software. And most of the examples in this talk I'm going to do from the user point of view. But again, I'll just re-emphasize, real software teams are diverse or should be diverse. And getting them to be high functioning teams is a really interesting aspect from a human perspective as well. Oops. Right, so I'm going to give you some examples now. Most of the rest of the talk is examples. So here's one example we've been working on for a very long time, which is how to make complex models easier for developers and, in fact, sometimes non-developers and users to use. So our kind of hypothesis or thesis, if you like, is that we need to provide more human-centric ways to interact with these complex models. We like to use visual metaphors. I like to draw pretty pictures, and my PhD supervisor, Professor John Hoskins, likes to describe it as things that are good to sketch on a napkin in a cafe. So John and I, when we worked at the University of Auckland, used to do a lot of our visual language design in cafes. It's a great place to do academic work, of course, or industry work too, and we'd sketch them on napkins. Anyway, a little digression. So we've built lots and lots of different approaches to building domain-specific visual language tools. Many of them for software engineering, so design tool generators, software architecture design tools, performance engineering tools, user interface design, implementation tools, requirements tools, testing tools, etc. But we've also developed a number of end user applications. I think I'm going to show you a couple of these later in the talk. So these are kind of specialized visual language tools, human-centric tools, that enable non-technical people, end users of the software, to build their own software solutions, essentially. So we've done this for statistical design, report generation, mobile health app generation. I'll show you an example of that, I think. Business process modeling and business process enactment and workflow systems, music, games, visual wikis, data analytics, and so on. So I'm going to give you a couple of examples now of these domain-specific visual language human-centric tools. First one's generating mobile health apps. Now you could apply this to generating websites. You could apply it to generating IoT-based health applications as well. This one's generating Flash executables of all things, because it's a bit old now, but you could apply it to quite a number of kind of IoT smart home type things as well. So we want to model e-health apps. We want to, in this case, generate a phone-based implementation. We've got two models if you like. One's to design the care plan. That's the kind of intervention, the way you help someone better look after themselves. And the other one is the visual model, the UI, if you like, that's going to visualize the care plan being instantiated. We then configure it for an individual, generate a mobile implementation. It's actually 100% code generated, this example I'm showing you, so there's no handwritten code. And it was designed originally for doctors and nurses to actually model and generate, so didn't quite work as we intended, but that was the idea, that you wouldn't actually have developers building these things, you actually have clinicians. And this one's an old one, it's about 10, 12 years old, so it's got non-existent technologies that are mostly generated. So here's a care plan. This is in the visual health care plan modeling language or something along those lines. It's for obesity management, so I'm kind of put on my COVID kilos here, so I need to reduce them. So I've got a number of ways of doing this. I've got dietary therapy, that's stop eating all the nice goodies that I've got sitting around on next to my desk here at home. Pharmacology, so I can take some pills. Physical, I can go for my run or my swim or whatever, and so on. So that's a care plan. That's a model of how to treat obesity in this case. And we can instantiate it down to a particular person. So I'm going to go for a swim for a certain length. I'm going to go for a run a particular time, blah, blah, blah. This is the visual language for the interface. It's not a very well designed one, but believe it or not, it's actually specifying a diabetes monitoring screen. I'm going to show you in a moment. we put these two models together with a sophisticated code generator, and it generates a full working app. So here's an example of the care plans, and I can select that. Here's an example of the glucose monitoring thingy. These are flash executables, but the tool could generate a couple of other mobile app implementation platforms as well. Now, this is pretty cool. This is model-driven software engineering. Unfortunately, the tool never took into account a bunch of human-centric issues. This is a kind of counterexample. So we got aging people use these things, but it used kind of language and a kind of a problem-solving style that didn't suit them. People of different cultures, there's some words on some of their screens, some ways of sort of presenting health information. It's a very Eurocentric version of health. And so people not coming from a European kind of descendant vision of health and well-being, it didn't suit their model of healthy living. Had some gender bias problems. I think it's even got he somewhere in there. And got some language problems. It's got all this jargon, both health jargon and kind of developer jargon, and so on and so on. So this is the kind of thing we want to fix. We want this kind of tool, but it needs to take into account this wide range of end user characteristics. We need to put them in the models. We need to generate either multiple apps that suit different users, or one app that can adapt to different people. And I'll show you a couple of examples of doing that in a moment. This is Bitaml. This is our big data modeling language, or something or other along those lines. So this is a way of modeling complex data analytics problems. The idea is to support multidisciplinary teams. So in a traditional kind of big data team or data analytics team, you'll have domain experts, data scientists, software engineers. You usually run on the cloud platforms, you cloud engineers, and sometimes other people as well. And they're all kind of quite different, and they kind of have very different ways of talking about big data and talking about analytics and talk about, you know, kind of particular problems they're trying to solve. So we developed a set of modeling languages, the idea being that all of these members of the kind of multidisciplinary team could share this common model and common terminology, model from a very high level down to a very detailed level their data analytics solutions. And we're, oh, whoops, where's my companies? I lost my companies. I had some icons there, but they're gone. So we've done this with a number of companies. So it's kind of a trialed and industry work as well. So here's some examples. So here's some of the languages that we have in this tool. So we've got a bunch of diagrams. This is a brainstorming diagram over here. So this is actually done with Vic Roads. So it's a traffic modeling problem for the people who run the roads in Melbourne. If you were in Melbourne with us, you'd have experience kind of going across roads and driving along them and so on, I'm sure. It's doing traffic prediction. So we're sucking a whole bunch of data from a whole bunch of sensors on cameras and roads, historical data. So this is data from those kind of black things they put across roads that gather lots of large scale transport data. It's taken live kind of data feeds as well as historic kind of traffic engineering information, and comes up with a predictive model about congestion. And the idea, of course, is to better manage the traffic light sequencing and so on to manage the congestion. Can't remember what kind of type diagram. This thing is a data diagram, and this is a technique diagram, and some other kind of diagrams. So there's a bunch of these different visual languages to model these problems. Again, this is well and good, but again, it doesn't take into account some interesting end user things. So when I produce a solution, I produce a number of things like what ifing and flow prediction and vehicle trajectory prediction, all that kind of cool traffic stuff. How do I present this to, for example, different kinds of traffic engineers, council members to decide to build a new road, different end users, you know, citizens that might want to know this and so on. So we need to take into account a bunch of these things to produce better end results for diverse end users. Here's a smart home example. So we've been very interested for many years about how to support particularly aging people, but also people with physical and mental challenges in their homes. The challenge in this situation is, again, people use software. We want to help them in this case, a smart home, you know, help them managing their challenges. But people react very differently to software in different situations. And one of the really interesting ones here is the emotional reactions. So again, smart homes, when you've got dementia, chatbots, etc. So we've used this kind of emotion-oriented requirements engineering, we call it, to try and elicit the different ways that these diverse end users react or might react to these software solutions, or in the smart home cases, a kind of IoT sensor, smart sensor solution, and try and reduce the kind of bad emotions and promote or support the good emotions. So here's an example of a smart home model. I've got, these are kind of negative emotions that might generate. I might feel monitored, controlled. I might be over dependent on others. I might feel the solution's inflexible. I might feel insecure, etc. And here's some good emotions. We want the elderly person to feel in control. They want to be independent living, want to feel empowered, comfortable, etc. And so we take a traditional goal model, which is kind of functional goals and quality goals, and we add in these different kind of positive and negative emotions that might be generated or might be encountered by the users while they're using, in this case, the smart home solution. And then we try and, as we develop the software based on this enriched emotional goal model, make sure that we support or increase these kind of good feelings and try and mitigate or reduce or get rid of these bad feelings. And we come up with an emotion-oriented design and implementation, essentially. So this is cool. Well, I think it's cool. But we're also interested in how would we enrich these kind of models with other kinds of human characteristics. So we've done some recent work on age, so how to model differently aged users and their needs for different solutions, so different interfaces, different workflow through the software because of their aging characteristics. We're very interested in gender issues. I mentioned the gender mag before. We're trying to use the same idea in that to gender debias these kinds of solutions, particularly again the kind of IoT based kind of smart home type solution, which again is almost all built by men and kind of designed by men, and in fact most elderly people in Australia are women. And then people have physical challenges. So how would I interact with the system? I'd like to interact perhaps by voice, but I might want to interact by gesture or touch. I might want to be able to support people that have mobility or English as second language. I might want to have a system that can speak multiple languages, if you like. To again, 1/4 of elderly Australians are English as second language, and actually often revert to their native language, their first language, as they get older. One of the interesting problems with software, it's always got problems, defects we call them in software engineering speak. One of the interesting areas that I've been working on for some time now is how to better manage these defects. It's kind of a sort of related to testing, but different. Testing finds defects and we've got to fix the defects. I'm much more interested, well, I'm interested in both the finding and the fixing, but probably more the fixing. We have functional and non-functional defects. We classify them as. So functional are things it should do, and non-functional are constraints on its doing. One of the really interesting under-researched areas is usability defects. These are problems how the user interacts with the software. We're interested in, or have been interested in, how do we find them, report them, and fix them? How do we improve the reporting? How do we improve getting end users, diverse end users, to be able to report? I'll show you an example of addressing that in just a moment. We're also really interested in persuading software engineers that it's a real problem. So I mentioned before that software engineers are different to most of their users. And often with usability defects, you find the software engineers just don't get it. Like, it looks fine to me, I can use it fine. Why are there all these end users saying it's a problem? And often the software engineers think the problems are quite trivial, but they have a major impact on the end users using it. And it's often because the end users are, again, older, so different gender, different language capability, different socioeconomic group, emotional reaction, personality, all those kind of things, different to the people who designed and built the interface. So part of this work, we've been building a new way of reporting these defects, and I've got a new PhD who's just starting to look at furthering that work and also looking at how to help software engineers better understand the defects from a human-centric point of view and fix them. So here's an example of a taxonomy we developed to have a much richer way of describing usability defects. There's actually several existing taxonomies that synthesize from, and some new stuff that we put in. Believe it or not, all the existing usability taxonomies, usability defect taxonomies, don't support things like phone interactions. They're all developed kind of the days before smartphones. So that's kind of interesting. Here's an example of one of our guided defect reporting forms. It uses a wizard-based interface to guide someone through reporting defects with the interface. Here's another example of giving more, so you can kind of see they work through this kind of a workflow for reporting. Most existing defect tools, you just dump a bunch of text, and that's all the developer gets back, and it's all the users given. This gives a much more structured way, based on that taxonomy, to structure the feedback. And here's an example of doing this for diverse end users. Here's a dark mode version to improve contrast. Here's a magnification of parts of the interface to improve sighted issue, and this one's got something else, but I forget. There's a voice interface too, so you can actually record with your voice the defects, and the voice will go back to the development team. So again, we're really interested in how, software is going to have problems. How do we help diverse end users better report the problems they're having, and developers better understand the challenges their diverse end users are having with their software, and help them fix it? One of the areas we've been working on, this is work with Xiao Lu from Deakin University, is large-scale systems that have large numbers of data generation and data sync devices, sensors if you like, and processing, sort of edge fog type architectures. We're very interested in the kind of implementation of workflow in such platforms, and how to performance engineer these. So earlier we did a lot of work I did with Yun Yang from Swinburne. We did a lot of work on improving the capacity and throughput and number of users, if you like, that could be supported by large-scale cloud applications. With Xiao, we've been working on how to do this for fog-based applications, which got obviously some relationships, but a lot of differences as well. So one of the scenarios that we've been working on is how to run workflow type systems that Yun and Xiao have worked on for a long time on like smart infrastructure, so kind of industry 4.0. So where you might have a great big factory with industry 4.0 sensors and actuators and controllers, literally thousands of edge devices, hundreds of edge servers, because these devices produce very large amounts, high volume data at source, and then coordinating them with a traditional cloud-based ERP type factory control system as well. Here's an example of a tool that Xiao's been working on, a fog simulator, or fog workflow simulator to be more precise. So it takes a workflow, a scientific workflow. So you might imagine that's useful in a lab environment or a factory environment. It's got a number of cloud servers. So these are kind of traditional large scale, large compute, large data entities. It's got a number of fog nodes. So these are kind of medium scale data and compute devices. There's a reasonable amount of data storage, there's a reasonable amount of compute, and a very large number of end devices. So these tend to be small compute, small data, but they might generate a large volume. They could be cameras, they could be audio things, they could be MRIs even, they could be infrared, a whole bunch of quite diverse devices that produce a large volume of data that needs to be processed in various interesting ways at the fog, and then ultimately at the cloud. This environment allows you to set up quite a sophisticated, quite a complex simulation environment and run the simulation, and in this case get examples. So here's some allocation algorithms that have been run, and you can get a sense of, here's a timing data, there's energy consumption data, and there's a cost formula that's involved in that as well. You can switch on and off various parameters and configure it in different ways. It's a simulator, but we try to run it as a simulator on real hardware. So the latest version has real hardware at the back end that you can run, again, simplified versions of the workflow and edge computation and data manipulation on, to try and get a real or realistic understanding of time and energy consumption. Again, so some really interesting questions here. What happens when we overlay this with, if those devices are being used in like the smart factory or the smart building environments? So smart buildings again have hundreds, if not thousands, of sensors now. How do things like data privacy impact this? When should I capture the data and when not? can I transmit the data from a fog node to a cloud node or not, depending on different end user privacy requirements. What about security, transparency, etc.? So there's very interesting implications for the simulation environment and the real environment based on putting some of these human overlays. We're very interested in deploying large edge-based applications. This is work with Nathan He and Fei Chen from Deakin and Swinburne. So we have some really good students at the moment working on a whole bunch of interesting aspects of edge computing. How do we distribute users? How do we distribute data? How do we cache data? How do we optimize performance for time, cost, throughput, response time, minimizing data duplication, etc., etc. And how do we adapt these things at runtime as people move around and possibly devices move around? So the devices, while some of the devices might be fixed, some of them may be quite mobile. They'll be on, like in a smart factory, they might be on forklifts, they might be on kind of the, kind of robot things that move about the factory and so on. So you have to take account of them, talking to different edge servers at different times, etc. So we developed a whole bunch of models of these kind of scenarios. Here's an example where we've got our kind of traditional cloud, and there's kind of course, a high degree of latency that you suffer when you try and connect to a cloud-based platform from one of these user edge devices. So the user edge devices would prefer to connect to these kind of edge servers, but the edge servers, of course, have some overlapping coverage. We've just recently done a NOMA 5G simulation to show you what can happen when you use a NOMA-based communication approach. Is very interesting. So we get, again, lots of servers here. There's lots of services running on both the cloud and the edge, and also on the end user devices. Users interact with multiple devices. How do we allocate these things around and optimize, particularly when we've got 5G connections where we're trying to manage cost, latency, throughput, and maximize utilization of the edge devices and the edge servers. Again, a really interesting one here is what happens when we then start to overlay again privacy issues, security issues, different users wanting different kind of performance, different user preferences, if you like. Wanting to use different kinds of devices, users with challenges, again, that need to use different devices that end up connecting to different parts of this edge network and so on. We've been working on smart city data for a little while. It's, again, one of my use case interest areas. One of the reasons is because, by definition, a smart city needs to support everyone. Okay, everyone's a citizen, and smart city solutions, both services the government provides and people consume, need to be consumable by everybody. So there's lots of interesting issues around accessibility, around supporting diverse people, language, age, gender, culture, etc. This bit of work that I'm going to tell you about in a minute is one where we tried to understand data coming from pedestrian monitoring sensors. So these are sensors deployed by the City of Melbourne, and you can freely go and get data about them. People walking across bridges, people walking down roads, crossing pedestrian crossings, and so on. And initially, the user base was planners. So these are people that kind of run the city council, run the smart city, to give them data from a diverse range of sensors about people's activities to help make the smart city run better, if you like. We also then got interested in, well, if planners can see this data, why not citizens? And what kind of ways might this data be best presented to citizens so they can make kind of decisions about what they do? Do I go into town today or not? Do I go to the office or not? Do I take that mode of transport? Do I go to that shop, or do I make use of that service or that one, et cetera, et cetera, et cetera? And again, it gets into really interesting, really large scale issues of data distribution, privacy, security, scaling these solutions, again, performance, number of users, number of sensors, number of edge nodes, all that kind of stuff. So as an example of a tool, one of my postdocs built some time ago in his PhD, which was looking at visualizing pedestrian count data in Melbourne, and then overlaying it with a number of other data sources. So there's count data, which is kind of what's being visualized in those kind of radial kind of thingies, and it changes as a 24 hours, so it changes during nighttime. It's pretty quiet, which might not surprise you. There's temperature overlay, so you can have a look at how does the if I change it to different temperature days. Yes, we do get to 40 degrees in Melbourne, not this time of year, but in kind of January, February. So, and we do get down to 0, by the way, in Melbourne as well. Does pedestrian usage of different parts of the smart city change based on temperature? We're interested in events, so you can select here different events. So what happens in Chinese New Year, where we have a big set of celebrations? What happens during election time, or other kind of Anzac Day, which is our kind of remembrance day for Australia and New Zealand, etc. And then there's different kinds of sensors in different places, so you can do some analysis of the different kinds of usage environments of the smart city. Again, we didn't look much in this work into some pretty interesting kind of angles here. How would different user age, mobility, capability, language even, and culture perhaps influence both their usage of the spaces, but then also the way we present this information to them potentially? So how could I use some of this information to make decisions about how I as a citizen go about using the smart city and the services provided to me? We've been working on recently some, and this was Data 61, and a student funded by them, some smart building issues, and particular interest in privacy and data privacy. These are buildings with lots of sensors, lots of, again, kind of edge nodes, or edge servers that collect the sensors and do various controllings of the smart building. And we want to develop a better informed consent model about what data is captured by the sensors, who can see it, what is done with it, and give users some control over whether it's captured and what is actually done with it. And then we want to simulate that. Again, we want to do this we want to actually retrofit our own office, our own lab, but COVID-19 got in the way of that. So here's a model on the left-hand side of a kind of a solutions, but this is one of our candidate solution spaces. So we've got voice-controlled things, we've got devices that are controlled by voice and gesture and so on. We've got mobile applications to kind of interact with it, tell you, hey, this device is trying to capture information about you. Do you want to allow it or not? We've got a dashboard, and we've got various kinds of both cloud and edge componentry that implement this. Here's a dashboard that simulates, this is actually my lab, which is my office, he says to himself. I can't remember, somewhere over there. Oh yeah, John's office, there we are. John's office, that's my office, I remember now. And when you go into the smart building, you can go in through a door and it'll sort of turn the lights on automatically. It'll capture some temperature information. There's a smart TV that I think actually you can speak to, and there's a voice controller somewhere, but I've forgotten where. And so you can see different parts of the building being modified. There's some HVAC kind of stuff. So there's a building control system kind of things, the temperature and lighting and stuff. And as I interact with a smart building, sorry, the implementation of this is using a nudge-based metaphor will remind me, hey, John, you've entered the door, you're now being monitored by your desk computer or something. Do you want it to do that? Or are you aware of this? Do you want to leave, etc.? So there's a bunch of protocols it goes through to try and inform you about what data is being captured by different devices, when, and what might happen with it. Again, we're also interested in then what happens when you've got a different user characteristics. So how do the different user characteristics perhaps changes? What if I've got a very different kind of view of privacy depending on my culture or my age? What if this system is assuming I'm a native English speaker, but I'm not? How do I have dialogue? What if it's assuming certain kind of jargon, etc., that I don't normally speak or don't understand? We've been interested in what I call end user development for many years. And I'm going to show you just one example of this, which is actually data transformation or data integration. So this has become, it used to be kind of something that was a bit more esoteric, but now it's become really popular because every smart kind of system needs data wrangling and data integration and so on. Data harmonization. So traditionally you'd write scripts to do this. You know, these are kind of some old style ones, but you'd write code basically to program a data integration solution. An alternative way is to actually do it visually, and I'll show you an example of a domain-specific visual language that we developed to do this for end users being able to program their own data wrangling and data integration solutions. So the meta model here is, again, the source and target mappings are XML-based ones I think I'm going to show you. This visual model. The visual models can take lots of different forms, and I'll show you a couple of examples of that. And then again, this is 100% code generator, the one I'm going to show you. So it generates the whole implementation of the data wrangling, if you like. And we've developed lots of, this is just one example of several we've developed. So here I've got a 2D layout. This is actually a CAD tool. This is a model exported by a CAD tool. I've applied over the top of it a two-dimensional visualization. So it gives you a feel for what the actual space looks like. This one is from an ERP system or something like that, so some kind of resource management system. That's using a tree-based hierarchical metaphor to show groupings and so on. Then what the user's done, they've dragged and dropped. So it's a domain expert, so it's a non-programmer, a non-software engineer, non-software developer. They've dragged and dropped what we call correspondences between one or more elements here and one or more elements here. And there's a whole bunch of rules and formulae and stuff you can specify, and we map basically the source data to the target data. I click a button, it generates all the code to do that. So it can take XML or JSON models in the source, and it can generate XML or JSON models in the target with no, it's a zero code, it's a no code, not a low code solution. Here's give you an idea of the power of it. So it is a data visualization tool. This is Minard's map. So this is Napoleon invading Russia with the Grand Armée in whenever it was, 1811 or something. And this is his kind of invasion route, and kind of the army's shrinking, as you see, by attrition, and then they kind of got defeated, and they kind of go back again. So this is all, by the way, specified again, 100% specified by data mappings and formulae and a code, an implementation generated. And I'm reusing a pie chart to show some kind of visualization here. So just to show you, it's quite a sophisticated kind of approach and tool. Again, this one doesn't take much of account of the user diversity. So some interesting question about what would happen if I had users of different human characteristics trying to use this. It's a one-size-fits-all solution, even though it's an end-user development tool. I probably need to better take into account a range of those user characteristics in the solution space, which is part of some work we're currently doing. All right, so that's all kind of fun. So where have we got to? Well, unfortunately, there's still a number of open-ended problems, as Raj alluded to at the start. Some of the things we're working on at the moment are part of some grants that we're fortunate to have, trying to address some of these issues, but many of them are larger scale problems. So first of all, software engineers often don't understand or appreciate human aspects, both their own, the team's different personalities in the development team, emotional reactions to design and implementation, even different genders and ages and backgrounds, etc. in the team, are well-known problems in actually engineering software. They also don't appreciate the end user human aspects. So they're different. Most software engineers are different to most smart city users, and therefore they produce solutions that suit them pretty well, but not always suit that well the diverse users. I was making a facetious comment, this comes from another talk. The grant assessors often don't appreciate this either. So the point I was trying to make is that when you're trying to do these kind of human-oriented studies, the grant assessors, the New Zealand one and the Australian one, my experience has been it's hard to persuade them, although again, maybe some recent successes we've had are counter examples of that. But most of the grants in this part of the world are assessed by engineers, and engineers don't appreciate many of the human aspects, ironically as well. Uh-oh, excuse me just a second. Enjoy. I'm just getting afternoon tea by my daughter. How's that for an advantage of giving a keynote talk from home? So just to prove to you I've been given that. Designing and conducting experiments with these people are hard. We have to find a range of representative end users. We have to find a range of people who are willing to help us elicit requirements, come up with designs, multiple kinds of designs and alternate ways of doing things, give us their open feedback about problems that we've got to address. So it's very time consuming. We need to access practitioners. We need to convince them and their bosses, their companies, that these things are real challenges. I'm waiting for the day that we get more companies sued for their software not supporting diverse people, you know, either accessibility or other diverse user issues, because that might wake their ideas up a bit better. Many of those areas are not well explored. So in software engineering, many software engineers are not very well trained in terms of, for example, user interface design or UX, user experiences. So they have some knowledge, but they're not experts. And even though in large companies, we might have UX experts in the team that can help them, smaller companies or people building, you know, mobile apps and even IoT solutions and so on, most of them don't have much experience at all in these issues and how to understand them deeply enough to come up with good solutions. I find them really challenging. They're much harder than my kind of automated software engineering kind of generate code type projects I like doing, but they're also very interesting, and I find them much more interesting than just a purely technical project. So the edge ones I was talking about, we've done sort of purely technical kind of work there, but these kind of human aspects of both the engineers of the edge solutions and the users of the edge solutions brings in a whole nother layer dimension that makes the problem much more complicated and difficult, but a lot more interesting to solve. Finding good students can be a little challenging, but again, we've been lucky to have lots of good ones. And I guess ultimately, why I was kind of really grateful that Raj asked me to come and talk to you today is we need to be working on this stuff as a community. So in software engineering, we've still got a long way to go, and the kind of tools we have and the techniques we have for evaluation of software and design of software and doing requirements capture is still nowhere near as good enough as we need to address some of these issues. And I think in the grid computing, the edge computing, the IoT computing areas, I'd apply exactly the same lens to that. I think we need to better support diverse end users of our IoT, grid, fog, edge-based solutions. And we need tools and techniques. We as a research and practice community need to build better tools and techniques to enable us to do that. So how are we doing it? Just to finish up. So we've got kind of two kind of key aspects, if you like, to our research program. We have the human-centric side and the model-driven side. So the top one is they're kind of looking at a whole range of different diverse aspects. I've just listed some of them there: emotions, physical, mental challenges, gender, age, culture, personality, enjoyment, etc. We want to model those. We want to capture this in requirements and design models. So we want to give software engineers tools and languages, taxonomies to talk about these things. And we want to reason about the completeness of these models. So we want to proactively say, oh, we didn't think about aging users, or people of different cultures, or people whose language proficiency might be very, you know, I've got a PhD, so my language proficiency in terms of using big words and so on might be quite different to someone else's. And so we need to incorporate those different capabilities and perspectives in our software design, our implementation, and our evaluation. Then again, in the model-driven side, we'd like to put these into models and put them into code generators, give developers better tools to use these extended models. We want to produce software that can maybe auto-adapt, so it can learn as you use the software. We want to allow end users, as I showed you in a couple of examples, to modify it themselves. Tell the software, hey, you're not doing it the way I need it done, do it differently. And then we want to provide better ways of giving feedback to users. So at the moment, again, it's just too slow. People are given software solutions that just don't work for them. It takes way too long to get that feedback back to the software engineers. Software needs to understand it and the improvements made. So, and then the software redeployed to the users to hopefully improve their lives, improve their work. So in summary, human aspects are pretty interesting of these software systems. And I dare say they're at least as interesting of IoT-based systems as well. Lots of scope for work. I hope my little paper that I wrote to go with the talk kind of outlines that. There's been some pretty interesting work done, but it's a long way to go. there's a lot of opportunity to apply other discipline approaches. Social sciences of various types, psychology, ethnography, etc. Ultimately, humans produce software and they use software. We need to incorporate their diverse perspectives, and smart city applications, smart homes, large edge fog systems. They're going to have very diverse end users. They're going to have diverse developers as well. They're complex and evolving, and we need to better support them to produce better systems. Thanks very much. Let's close my door.
Thank you, John, thank you very much for this interesting keynote talk. So I guess now we let others to ask a question. So any of you like to ask question, please unmute and go ahead.
Raj, they cannot unmute themselves. They should send their question to you or one of the co-hosts.
Oh,
yes.
I see. So can't we do unmute all, something like that? Can you click on?
Yes, I can do that, but maybe it is not very easy to manage that.
Yeah,
okay,
you can
so
unmute all for 5 minutes, then we'll.
I activated. I activated, so other.
All right.
Everyone
so
can unmute.
So John, you can have a look at chat box. So there is a question.
I've got the chat box. If anyone wants to type a question in the chat box, they're welcome to do that.
Oh, somebody typed already. So I can read out that question. What methods do you use your work to study human behavior, like interview, qualitative or quantitative?
Yeah, look, we use mixed methods. So we like to watch people. So that's kind of observation. We do surveys and interviews. We deploy systems and again observe people using them. We instrument them as well, so we capture data from people using systems. We like to build prototypes, but that living lab approach I just talked about, we want to build the prototypes in a different way. Typically we have solutionism, which is where we technical folks, oh, that's a good idea I've come up with, oh, let's build something and see if it works. We want to kind of more tightly integrate diverse stakeholders, diverse end users of those solutions in that cycle and treat them all as a first-class citizen. So at the moment in software, we have them and us. So most of us are probably us because we're all software developers of one sort or another. And everyone else is a them. And we treat them like, we even talk about users and so on. So I think that's the wrong way of thinking and building these kind of, these kind of solutions I talk about at the bottom point. We need teams that are multidisciplinary, tightly integrate all the members of the team, treat everybody just as important as everybody else, whether you're a builder or a user or person who's paying for it, or whatever. And develop better mechanisms to have that dialogue and that collaboration through the process. So that kind of living lab approach has been used quite successfully, particularly in Europe, to build e-health systems for quite some time. And we're trying to apply that model to this kind of model-driven, human-centric, model-driven software engineering idea. To see if it works. Now, it might not work, but that's what we're trying out as an improved approach to implement our methods, if you like, in this domain.
Thank you, John. So I have a question. When we look at these diverse computing infrastructures, such as edge, fog, and the cloud, and then you need to build this software system, not only take diverse needs of different users, but also diverse underlying infrastructure. So what is your suggestion on how do we engineer software with minimal effort that can work across all these diverse computing infrastructure?
So it's a good question. So the what I call is software engineering for edge. So that simulator I mentioned, that fog workflow sim, I went to the automated software engineering conference. I actually presented the demo paper myself because I've been in that community for a long time. Almost nobody understood what fog was. In fact, I think no one knew what fog was. This is software engineering. This is one of the top software engineering conferences. Almost no one knew what edge computing was. I think maybe one or two people have vaguely heard, but didn't know what it was. most people have heard of cloud, and kind of maybe a number of them had been involved in cloud design, but surprisingly not that many. So one of the problems we have is if we talk about better engineering techniques to build software to run on these heterogeneous platforms, the kind of leading software engineering researchers, most of them don't understand what fog is, what edge is, some of the kind of problems these diverse networks and infrastructures and compute and data storage, etc. bring. So that's a real worry. And you might say, well, maybe that's a problem with software engineering, but I was surprised how I had to explain to virtually everybody what a fog concept was, what an edge concept was, etc. And to solve that, we need that community working with this community much more. And we probably need this community working with perhaps some of the electrical engineering out of the network. I just talked about the NOMA paper we've just recently published. It was interesting. I learned a lot about NOMA-based 5G networks and that work, and some of the really interesting characteristics. The way you can manage these kind of edge connections with a NOMA-based network was totally different to a a WLAN or other kinds of network solutions. So I think there's some really interesting emergent things there. And then, of course, in sort of the sensing community, lots of really interesting new ways of capturing data that have really interesting characteristics. And we need to better understand those characteristics, both functional and non-functional, to integrate them into these kind of smart city, smart home, industry 4.0, etc. Solutions that we're trying to produce.
Thank you, John. So there is one more question here on the chat box. So the question is, can IoT device be used to collect data to capture human behavior without compromising privacy?
Look, great question. We've got a couple of projects that we're using IoT devices to capture things like the sort of face recognition, but to try and decide things like emotional reactions and so on. We're also interested in, again, by using IoT devices. I'm wearing one right now on my wrist. Can I tell I'm getting stressed? Actually, I'm feeling great, by the way. It's great. It's lovely talk. It's a great privilege to talk to you all. But if I'm feeling stressed using software, can I then adapt the interface of the software, maybe the workflow? Maybe we're working with our people that do the assessment software at the moment. How do I reduce the stress of assessment? Now you might say that's like oxymoron or impossible problem. How do we make students less stressed in exams? Essentially, is what I'm saying. But I'm serious. Can we use a sensor to say, oh, the student's getting a bit worked up. They're getting, they're not going to perform as well. Can we give them an easier question or move on to a different part or something proactively? Can the software learn that from a IoT type data input and then help them to better use the software? Reduce stress, increase enjoyment, adapt to their eyesight challenges or hearing challenges, or recognize they've got a different cultural background. I shouldn't be using these terms that are inappropriate or offensive even in some cultures. Recognize they need different kind of terminology, those kind of things. So we've got, again, an e-health project that's also capturing a range of sensor data and sharing it. There's major privacy issues and lots of kind of approaches that people are using on device only processing. So you send no identifiable or re-identifiable information off the device. It's got challenges, as you're probably all aware. That nudging basing, so we assume that things actually think nothing's private to some level, but we give people more awareness of where privacy breaches from their own personal view of privacy might take place. And everyone's got a different view of that, it turns out. And then there's sort of policy issues as well. So one of the projects one of my students has been working on is privacy policies of COVID-19 apps and social media apps. So a lot of people are worried about their privacy with COVID-19. So my wearable or my phone might be being used to capture information about my COVID-19 status. Turns out they're much safer the privacy policies are much more rigid, much more locked down than Facebook. And I happily go on Facebook and exchange really intimate things about myself any day and so on. And you don't want to keep using Facebook if you read their privacy policy and think about what they could be doing with your data. So the perception of privacy and privacy issues is a really interesting one in this space. And again, we need to work much closer with the security people and the privacy people who understand this deeply. Someone's asked me a question directly. Do you want me to answer a question that's in my chat?
Yeah, sure. You can answer some. So you can take one more question.
Which definitions can you refer to make it clear what is the difference between fog and edge? Cisco NIST or open fog definition? I'm gonna show my ignorance and say I don't know the answer to that. So anyone who knows the answer, which has got the best definition? I tend to use fog and edge interchangeably, and I know that's a bit naughty, but I'm a software engineer, not a fog engineer. So I tend to think of them as analogous things, although they are different. So again, I think then cloud, when does the cloud end? The edge begin, the fog begin, the device begin? I think there's different definitions that I've seen. And what I try and do is try and explain, I mean, this is this part of the solution space, this is this part of the solution space, this is this part of the solution space. And hopefully the reader can interpret that with their own lens on that. Do you know the answer to that question, Raj? Just
yeah. So the pure edge, what we call. So in which case the data that captured by IoT, you process on the edge. Don't worry about cloud or any intermediary. That's what we call pure edge computing. Then moving to fog. So fog means not only use edge but also use the intermediate computing capability. And whenever necessary, you also use cloud. So this is how people are promoting. But I agree with you that some are using interchangeably, some are using purely, and some are driven by what is pushed in industry. Right now, it seems like edge is as a word that is pushed much more prominently, and so therefore they say edge cloud, edge data center, edge computing. So it is right now it is a bit of a mix, like what you said. This is what I need to do here, get it done. So it doesn't matter what you call. But yes, edge is getting more popular for that same model. Yeah. So yeah, there are a few more questions. One, maybe you can give brief answer. So what criteria are used to evaluate human aspect of software engineering?
So what was the used to what?
What criteria are used to evaluate?
Oh, to evaluate.
Human aspect?
So there is no existing taxonomy of criteria, if you like. So one of my laureate plans is a taxonomy of human aspects in software. Now, it's a bit of a grandiose vision. We're actually starting to build up such a taxonomy. So from a whole range of sources, from developer discussions, app reviews, various kinds of user reviews, Stack Overflow discussions, and also synthesizing from requirements documents. We've built up a number of examples of quite a wide range of these, I call them human aspects. But there doesn't exist an agreed kind of, nomenclature, taxonomy, or whatever you want to call it. And so then evaluating them, if I'm saying I'm evaluating accessibility, is an interesting one. So it comes from HCI and that kind of space. But when software engineers talk about accessibility, they often talk about a bit of a different thing to what, say, an HCI person would. So there's also cross-disciplinary different language. So in terms of evaluating them, I think first of all you got to define what you're doing. It's a bit exactly the same as the edge fog kind of definitions, and then you say, okay, I've defined. I'm going to do age, for example. Well, age is actually surprisingly, you think it's just your physical age, but age actually has got a number of different meanings, again, in different cultures and environments that you use it. So you have to define what I'm meaning by age, an end user's age, and the kind of things I'm then testing against. So our social media, our online shopping, online e-commerce one, we defined age bracket ranges, and we particularly compared quite old people, over 70, silent generation, to others, and that was the age bias thing we were analyzing in that book.
So thank you, John, for answering all the questions. And of course, there are few people are typing. That's all right. So in interest of time, I like to conclude this session. So again, thank you very much for sharing your nice, informative, and inspiring examples of how software engineering can be improved by taking human needs, and also how do we build them for different computing models and emerging cyber physical system and their application. Thank you again. Thanks, John.